So let's move on to the fundamental theorem of arithmetic. Boom, 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 boom. So before we actually state the theorem, let's play with some things. Let's play with repeated factorization. Here's what I mean by that. Right? So when scientists were studying like the natural world, things, right? Whiteboard markers, wood, human bodies, whiteboards, right? When scientists were studying things back in the day, right? A big thing they wanted to know is how far could you break something down? So for example, if you look at this wood, right? You can't see the wood. If you look at this wood, wood was made of trees, a living thing. You break wood down into cells, right? In cells, we broke it down into molecules. The molecules can be broken down into atoms, right? Like science when they thought about what are things actually made of fundamentally, right? They came down to atoms. And I guess we could go to subatomic particles. We like to stop at atoms, right? The point is it came down to atoms. The atomic theory, that everything's built of atoms. And there's different types of atoms based on the periodic table, right? And all of those different types of atoms can be put together to form everything we know about in the natural world. All by just looking at what things become when you break them down. How far can you break something down? Let's do the same thing here with numbers. Because one very useful way to break down numbers is by factorization, factoring them. So, for example, 54, right, equals 2 times 27. It can be broken down into 2 times 27. But can you break those down further? Two, not so much.
9 and 3.
9 and 3, right? Yeah, this is going to be 2 times 9 times 3. Can you break that down?
2, 3, 3, 3.
Yeah.
3? I don't know how many 3s I said.
Yeah, be like that. The 54 can be broken down to 2 times 3 times 3 times 3. And actually there, we can't go any further. Because 2, 3, 3, and 3. Well, I guess we could call it like 1 times 2 times 3 times 3 times 3. But we can always add a 1. We're not really making it smaller. We're not breaking it down into smaller parts necessarily. So let's just leave it like that. Ta-da! 32. 32 equals 2 times 16. Absolutely, then 2 times 8. It should be broken down at 2 times 4. It should be broken down at 2 times 2 times 2 times 2. So get rid of those parentheses. And then we can't break down any further. Or we could do 66. Now you break it down to 2 times 33. Can that be broken down any further?
11 and 3.
11 and 3, yeah. 2 times 3 times 11. But then that can't be broken down. 11 can't be broken down into anything. 3 can't be, and 2 can't be. We can't like melt those down into smaller things. So we're done. Or we have 57, which kind of looks prime, but actually 5 plus 7 is 12, which is a multiple of 3, meaning we know 57 is actually divisible by 3. This is 3 times something, and it's 29. Yeah, that works out. But both 3 and 29 can't be broken down any further, so we stop there. The point being, into their like atomic components where you can't break them down further. right? What are 2, 3, 3, 2, it's 2 and 3 here, we have 2 here, we have 2, 3, and 11 here, we have a 3 and 29 here. What are 2, 3, 11, and 29? What do they all have in common?
They're prime.
They're primes, right? We can keep breaking numbers down until we get to their prime components. And then by definition, it can't be broken down. Remember, a prime, for all n and z, n is prime if and only if n is greater than 1 and a divides n only if a equals 1 or a equals n. The point being, right, n is prime, it's bigger than 1, and its only divisor is 1 itself. Meaning it can't be broken down any further by definition, right? So we keep breaking numbers down until we get to their prime components, because if we're not at their prime components yet, right, if we break it down to a number that's not a prime, like 33, well, by definition of not being a prime, it has some non-trivial factor, some factor that's not 1 or itself, like 3 and 11 in this case, so they get down further. And this is exactly what the fundamental theorem of arithmetic says. The fundamental theorem of arithmetic, otherwise known as unique prime decomposition theorem. What composition? Composition theorem. It says this: for every integer greater than 1, or I'll say every greater than 1 can be expressed uniquely as a product of primes. And uniquely is a big word there. Or it's not a big word, it's kind of a big word. It'd be a nice Scrabble word, but I'm saying it's an important word. Because 54 equals 2 times 3 times 3 times 3. Yeah, 2 times 3 times 3 times 3. But there's no other way you could write this as a product of primes that would equal 54. And that might seem obvious, but think about this, right? For example, 12 equals 2 times 6, but it also equals 3 times 4. So there's multiple ways to express 12 as a product of numbers. But there's only one way to express 12 as a product of prime numbers, up to the order you put them in. I'll say up to order of factors. Because of course, like you could write 54 as 3 times 2 times 3 times 3, right? That's kind of cheating. Like obviously these are the same. We're talking about different as in they actually have a different prime in them or a different number of primes. So yeah, the point is the way you write them as product of primes is unique. No other way to do it up to ordering. Any other questions? Are there any questions on what this means? Like what it technically means? It's huge. This right here is incredibly. Oh, we have a question in the chat. Yes, we ignore the possibility of always multiplying by ones because one is not prime. So one is not prime, and so it wouldn't be like it wouldn't be a product of prime. So I mean, what I mean by that is like if we wrote 54 as 1 times 2 times 3 times 3 times 3, this is no longer expressing it as the product of primes because 1 is not prime. So it kind of takes care of itself. And this is exactly why we need to use integers greater than 1. Because the only real way to express 1 is 1, right? There's no way to express it as any other integers, really. Positive integers, at least. And so we can't express it as a product of primes. Because 1's kind of like the base. You can't really break it down. But, yeah. So technically what this means is exactly what it says. Every integer greater than 1 can be expressed uniquely as a product of primes, which we can put formally as for all n and z, I'll say for all n and z, I'll actually use just trying to say all integers greater than 1. Integers greater than 1. There exists unique, or remember the parentheses means unique. P1, their pk primes such that n equals p1 times pk. That's what I mean technically, but like just from the heart, right? This is incredibly. It tells us something kind of crazy about the integers, and that is they have these atoms, kind of. The primes are like the atoms of the integers. Just like how everything in the real world can be built from atoms, every integer can be built from prime numbers. And that has a ton of consequences down the road. Integers work and how a ton of things work. Full. Can I erase this? I think so.